Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper for exam for February-March 2017. So let's get started. Question 1 says Figure 1.1 shows the axes used to plot a distance-time graph. On Figure 1.1, draw graphs for an object that is moving with constant speed and label this graph A, and another one with decreasing speed and label this one B. So speed in a distance-time graph is equal to the gradient or the slope. This means that for a constant speed we need to draw a straight line with constant slope. It does not have to start at the origin, but it must be a straight line, and we label this one A. As for the other one, we have a decreasing gradient for decreasing speed. So we start with something more vertical and we end with something more horizontal, and we label this one B. Part B says Figure 1.2 shows the axes used to plot a speed time graph. On Figure 1.2, draw graphs for an object that is I moving with constant acceleration and label this graph S, and another one moving with increasing acceleration and label this graph T. So for constant acceleration, again, the acceleration here is equal to the gradient or the slope. So we must draw a straight line to represent a constant gradient, and we label this one S. And for increasing acceleration, we start with something more horizontal and we end with something more vertical. So it will be a curve like this, and we label this graph T. Part C says a plane is at rest on an airport runway. The brakes of the plane are released and the engine of the plane provides a constant accelerating force. Using the following data, calculate the takeoff speed of the plane. Ignore any resistive forces. We have a constant force of 56,000 newtons and the mass of the plane is 16,000 kilograms, and the time to travel along the runway is 16 seconds, and we need the final speed, and the initial speed was 0. The final speed is unknown. We need the acceleration if we have the time to get the value of the final velocity, and acceleration can be found as force divided by mass or resultant force over mass, and the time was given already as 16. For the acceleration, we can divide 56,000 by the mass 16,000. That gives an answer of 3.5 meters per second squared. And then using this data, we can use the equation v equals u plus at to get v, the final velocity. So 0 plus 3.5 times 16. That gives an answer of 56 meters per second. Question 2a says explain why momentum is a vector quantity. We say that it has magnitude and direction. These are the things that define a vector quantity. Part B says the crumple zone at the front of a car is designed to collapse during a collision. In a laboratory test, a car of mass 1,200 kilograms is driven into a concrete wall, as shown in figure 2.1. A video recording of the test shows that the car is brought to rest in 0.36 seconds. When it collides with the wall, the speed of the car before the collision is 7.5 meters per second. Calculate first the change in momentum of the car. The change in momentum is equal to the mass multiplied by the change in velocity. The mass is 1,200 and the final velocity is 0. Initial velocity is 7.5. This gives an answer of negative 9,000 kilograms meters per second, or we can use another unit, Newton second. And the negative here represents that the momentum of the car decreased. Double I says calculate the force acting on the car. The force is equal to the rate of change of momentum, or change in momentum divided by time. We have the number of the change in momentum 9,000 and the time of the collision was 0.36. This gives an answer of 25,000 Newton, or 25 kilonewtons. Part C says a different car has a mass of 1,500 kilograms. It collides with the same wall and all of the energy transferred during the collision is absorbed by the crumple zone. The energy absorbed by the crumple zone is 4.3 times 10 to the power 5 joules. Show that the speed of the car before the collision is 24 meters per second. Now when moving, the energy is mainly kinetic. So 4.3 times 10 to the power 5, that is kinetic energy. And we can use kinetic energy is equal to half mv squared to get v, the speed. Substituting, we have 4.3 times 10 to the power 5 is equal to half times 1,500 the mass times the unknown speed squared. So moving everything to the other side, 4.3 times 10 to the power 5 times 2 and then divided by 1,500 is equal to the speed squared. So we square root that to get the value of the speed. And the speed will be equal to 23.944, which is approximately 24 meters per second as mentioned in the question. Double I says suggest what would happen to the car if it is traveling faster than 24 meters per second when it hits the wall. The change in momentum to rest will be greater, so the force on the car will be greater. This will cause more damage to the car. Question 3a says a stationary object is acted upon by a number of forces. State the conditions which must be true if the object first does not accelerate and second does not rotate. For no acceleration, we need no resultant force, and for no rotation, we need no resultant moment or torque. Part B says figure 3.1 shows a boat that has been lifted out of a river. The boat is suspended by two ropes. It is stationary, so it is in equilibrium. The weight of the boat acting at the center of mass is 24 kilonewtons. The tensions in the ropes are T1 and T2. Determine first the moment of the weight of the boat about point P. So we consider point P to be the pivot here, and we have the force and perpendicular distance from the pivot. We calculate the moment as force multiplied by the perpendicular distance, so 24,000 newtons multiplied by distance 0.40. That gives an answer of 9,600 newton meters, since we multiplied force by distance. Double I says calculate the tension T1, and triple I says calculate the tension T2. For this kind of question, since we are using moments and equilibrium, first we use the principle of moments, that the clockwise moments are equal to the anticlockwise moments about a certain point. We can use the same point here, P2, since we don't know T1 and T2 is also unknown. We can use the idea of a force passing through a pivot will have no moment, so T2 will not be included in the solving of the problem. Now, when considering P as a pivot, T1 is creating a clockwise moment and the weight is creating an anti-clockwise moment. We already calculated that moment. Now we can substitute in clockwise moments are equal to anti-clockwise moments about P. For the clockwise moment, the tension T1 is at a distance of 1.2 plus 0.4 from the pivot, the whole distance from T1 to the pivot. And on the other side, the anti-clockwise moment is caused by the weight is 9,600. We then divide by this bracket on the right side to get the value of T1. This gives an answer of 6,000 newtons. Now, since we already got T1, now we can use the idea of resultant force is equal to 0, or upward forces are equal to downward forces. We have two upward forces, T1 and T2, and one downward force. So the unknown T2 plus T1, 6,000, is equal to the downward force, 24,000 newtons. We then subtract 6,000 from 24,000 to get an answer for T2, 18,000 newtons. Question 4 says figure 4.1 shows a Galilean thermometer. This thermometer is used to measure the approximate temperature of surrounding air. We have 5 bulbs here labeled A to E, each with a temperature written on it. The glass cylinder contains water. When the temperature of the water changes, so does its density, because as temperature increases, objects expand, and when volume increases, density decreases. Each bulb has a label printed with a temperature as shown in figure 4.1. The bulbs have different densities at 21 degrees Celsius. Only bulb A is at the bottom of the cylinder. Explain in terms of density why bulb A is at the bottom of the cylinder and the other bulbs are floating. We start by saying that the density of bulb A is greater than the density of the water, while the density of the other bulbs is less than that of the water. Part B says the temperature of the surrounding air increases to a temperature above 23 degrees Celsius. Suggest one reason why there is a delay before the temperature of the water itself inside the cylinder increases to 23 degrees Celsius. That's because the water in the cylinder is insulated from the surroundings somewhat, because the glass of the cylinder is actually not a good conductor, or we can say the glass of the cylinder is an insulator or not a good conductor. Double I says explain why after this delay bulb B sinks. Assume that bulbs do not expand, which means that the density of the bulb itself does not change, but the density of the water now changed as it expanded. We say as temperature increases, the water expands and its density decreases. Now we say the density of the water became less than the density of bulb B. That's why it sank. Question C says bulbs A, B, and C are now at the bottom of the cylinder. Bulbs D and E are floating. State the possible temperature range of the water in the cylinder. Now A, B, and C have a maximum temperature of 24. D and E have a minimum temperature of 26. So the temperature must be between 24 and 26. That is the answer here. We write between 24 and 26 degrees Celsius. Question 5 AI says state 2 ways in which evaporation is different from boiling. First, boiling occurs at a certain temperature and evaporation occurs at any temperature. This is the first difference. The second is that boiling occurs through the whole liquid while evaporation occurs at the surface only, not through the whole liquid. Double I says give one example of a change of state which does not involve boiling or evaporation. We can say melting, or the opposite, freezing, or condensing, changing from gas to liquid. Section B says the graph in figure 5.1 shows the variation of temperature with time for a substance that is initially liquid. State what is taking place at points A, B, and C. You should say what changes of state, if any, are taking place. So for A, that's a change in temperature, or we can say decrease in temperature in liquid state, since we started with liquid. In B, the temperature is constant. That means that there is a change in state and we started with liquid and the temperature was going down. So this is freezing or changing from solid to liquid. The last part, the temperature was decreasing, which means we already changing from liquid to solid. At point C, we have a decreasing temperature and we already changed to solid. So we say decrease in temperature in solid state. Double I says suggest why the graph is steeper at point C than at point A. At point C we were solid, at point A it was liquid, and the temperature drop was faster at C. That means that the solid of this material has a lower thermal capacity, which means that it needs less energy to heat up and loses less energy to cool down. That's why it cools quickly. Question 6 says, figure 6.1 shows apparatus that is used to demonstrate some effects of transfer of energy by radiation. The glass bulb painted matte black, the shiny glass bulb, and the spaces above the liquid in the tube, which is U-shaped here, all contain air, and there is a heater in between the two bulbs, so it will emit heat radiation towards the bulbs. The heater glows red when switched on. The heater is the same distance from each bulb for fair comparison. State the two types of radiation that are emitted by the heater. So for a heater, we have infrared radiation, that's heat radiation, and it glows red, so we can say red light or visible light. Part B says before the heater is switched on, the liquid levels in the glass tube are the same. State and explain any changes in the liquid levels that take place when the heater is switched on. So for the heater in between two bulbs, one painted black and one painted shiny, or it is shiny glass, the black surface absorbs heat faster than the shiny surface. So we start from there. We say as current flows through the heater, it emits heat radiation or infrared radiation, and then we say the black bulb absorbs heat faster than the shiny bulb, so the temperature on the left side, the black side, becomes greater than the right side, exerting higher pressure on the left side of the liquid, so it drops, and the right side rises because the liquid is incompressible. So if you push the level on the left side, the level on the right side automatically goes up because it has no space to flow except this way. Question 7 says, figure 7.1 shows an object and its image formed by a converging lens. One ray from the tip of the object to the tip of the image is shown. Figure 7.1 is drawn full size. Place a tick in all boxes that correctly describe the image. Now this image is inverted and it is smaller than the object, and since it is formed by the real ray, then it is a real image. So it is diminished, inverted, and real. Now part B says on figure 7.1 draw a ray passing through a principal focus of the lens from the tip of the object to the tip of the image and label the principal focus F. We can measure the distance or the length of the object and measure the same distance on the central line of the lens to draw a line that is parallel to the principal axis to the center of the lens. And then from this point we go to the image to form the image, and the point where the line passes the principal axis is the focal point F. And we draw the arrows to show the direction of flow of light. Part C says use the ray you have drawn in B to determine the focal length of the lens. We can use a ruler to measure this distance since it is drawn full size. Not all of you will get the same exact number. For this diagram, we have a distance of 3.2 centimeters. So that's what I'm going to write, 3.2 centimeters. but you might have a different value. Part D says draw another ray not passing through a principal focus, so we do not know this one, of the lens that passes from the tip of the object to the tip of the image. We know that it will go out of the tip of the object and will reach the tip of the image. So we start with a line from the object going towards the lens at any point at the center of the lens, and then from this point we go to the tip of the image and we draw the direction of flow of light. Question 8a says a transformer consists of two coils of wire wound on a core. Suggest the material from which the two coils are made and state the reason for using this material. For the wire we use copper because it is a good conductor or good electrical conductor. Double I says suggest the material from which the core is made and state the reason for using this material. The core is made of iron or soft iron because it is a soft magnetic material. It can be magnetized and demagnetized quickly. Part B says figure 8.1 represents the system of transmission of electrical energy from a power station to a home that is a long distance away. State the difference between transformer X and transformer Y. Transformer X receives 22,000 volts and gives out 132,000 volts. Transformer Y receives the 132,000 volts and emits 240 volts only. So this increases the voltage, this decreases the voltage. So X is a step up transformer and Y is a step down transformer. Double I says explain why a very high voltage is used for transmission over large distances to decrease energy losses, because as voltage is stepped up, the current in the secondary coil decreases, which decreases the heating effect or the heat losses in the cables. And according to power loss is equal to I squared R, since the current is already decreased, we do not need to decrease the resistance. So we say, and there is no need to use thick cables or thick wires to decrease the resistance, which causes power losses. Triple I says suggest why the voltage for use by a home consumer is 240 volts and not a much higher value, just to be safe to use, because a high voltage will create a high current and the high current causes much damage. Question 9 says figure 9.1 shows a graph of current against potential difference for a filament lamp. Part A says state what happens to the resistance of the filament of the lamp as the potential changes, first from 0 to 1 volt and then from 1 volt to 8 volts. From 0 to 1 volt it was a straight line and then it curved towards the potential difference axis. So a straight line states that the resistance is constant or does not change. And when the curve bends towards a potential difference, this means that it needs more energy, so its resistance is increasing. The more it bends toward the axis, the higher the resistance. Part B says at normal brightness, the potential difference across the lamp is 8 volts. Calculate the normal brightness. Calculate for the normal brightness the resistance of the lamp. Resistance is equal to voltage divided by current. We have the voltage and we can use the graph to get the current at 8 volts. This value of the current is actually 0.72. So we divide 8 volts by 0.72 amperes. That gives an answer of 11.1 recurring. So we can say that it is approximately 11 ohms. Then we need the power of the lamp. Power is equal to voltage multiplied by current, and we have the voltage and current. 8 times 0.72. That gives an answer of 5.76. We can approximate that to 5.8 watts. Part C says 5 of these lamps operating at normal brightness are connected in parallel to a power supply. For normal brightness, it needed 8 volts, so all lamps need 8 volts. Determine the electromotive force of the power supply. In parallel, the voltage does not get divided, so we need an 8 volt supply, no more. Double I requires the current from the power supply. Now each branch of these will have a current of 0.72 at 8 volts, and we have 5 of them, and the 5 currents will join together to go through the supply or come from the supply. This means we multiply 0.72 by 5 to get the total current. So 0.72 times 5, that gives an answer of 3.6 amperes. Question 10a says describe in terms of particles and the terminals of the battery the movement of charge in an electric circuit. First we say negatively charged electrons. These are the particles that move from the negative terminal because they are repelled through the circuit to the positive terminal of the battery. So if we have a battery like this and the circuit included a lamp, for example, the electrons will move this way through the circuit to move towards the positive terminal of the battery, and the current moves in the opposite direction. Current moves opposite to a negative charge. Now part B says figure 10.1 shows a lightning flash between a cloud and the ground beneath. The charge built up on the cloud before the lightning flash is 0.60 coulombs. This charge is completely transferred to the ground by the lightning flash in 5.0 times 10 to the power negative 5 seconds. Calculate the current between the cloud and the ground. Current is equal to the charge divided by the time. We have 0.60 divided by 5.0 times 10 to the power of negative 5. This gives an answer of 1.2 times 10 to the power of 4 amperes, which is a huge current. That's why lightning causes a lot of damage. Double I says the potential difference between the cloud and the ground during the lightning flash is 2.5 times 10 to the power of 8 volts. Calculate the energy transferred during the lightning flash. We can either use energy is equal to VIT or energy is equal to VQ, which is voltage multiplied by charge. And we have the voltage 2.5 times 10 to the power of 8 and the charge 0.60. Just in case we calculated the current wrong, we used the givens in the question. And the answer will be 1.5 times 10 to the power of 8 joules. Triple I says suggest what happens to the energy calculated in B double I after the lightning flash has gone. We can say that it is converted to light in the lightning and sound, and then eventually converted to heat after the light and sound dissipate. Question 11 says a radioactive source is placed 20 millimeters from a radiation detector as shown in figure 11.1. The initial count rate recorded by the detector is 150 counts per second. Without anything between the detector and the source. A sheet of paper is placed between the source and the detector. The count rate recorded by the detector falls to 60 counts per second, so the change here is 90. With the paper still in place, a magnetic field is set up perpendicular to the direction of the radiation. The count rate recorded by the detector falls to 20 counts per second, so this change here is 40. The count rates have not been corrected for background, and the background count is measured as 20 counts per second, so the final reading was actually equal to the background. Now, the piece of paper can stop alpha particles but cannot stop beta and gamma, and since some of the radiation was stopped, then alpha particles actually was emitted from the source and then was stopped by the paper. Now, the remaining was either beta or gamma or both, and since the magnetic field deflected some of the radiation, this means that there was beta particles and gamma radiation would not be deflected by the magnetic field. But since the final count rate after placing the magnetic field dropped to the background radiation, there is no gamma radiation. So part A says state the evidence that each type of radiation is present or absent from the radiation emitted by the source. For alpha particles we say present since it was stopped by the paper, and for beta particles we say also present since it could pass through the paper and was deflected by the magnetic field. As for gamma rays, absent or not present, since the remaining radiation was equal to background levels. Part B says determine how much of the original count rate of 150 counts per second, if any, is due to each type of radiation. Now, after the paper, we dropped from 150 to 60. So that was alpha particles, and the difference between 150 and 60 was 90. And after adding the paper, when we added the magnetic field, the radiation dropped from 60 to 20. So the difference is 40, and that we said was caused by the beta particles. So beta is 40, and there was no gamma rays emitted from the source, so we say the answer here is 0. So this was the end of the exam. I hope you enjoyed this video and found it useful. If you did, give the video a thumbs up and subscribe to the channel, and I will see you in another video.